Okay, so we have question 9. It says the diagram below represents a current carrying conductor, and then it says draw the magnetic field pattern around this conduct. So we are shown a diagrammatic representation of this conductor here, and let's come to understand what this all means. So here we are given that if we are to indicate the direction of the current with this line here, this blue line here, this would indicate that the direction of the current is going into the page. And then if we see a dot here, this would indicate that the direction of the current is out of the page. So a way to think about it is if you're an observer here, so let's say this is an observer, and then now we want to take this pen here and use it to indicate the direction of the current. So if this is the page here, if you are looking at your pen from above, then this is what you see. So let's indicate here, this will be the tip of the pen and this will be the back of the pen. So if you are looking from above, this is what you see. You see the X, right? So this would say this is away from the observer because now the pen is going away from your eyes, right? So now this is into the page. It's going away from your eyes and into the page. But then if you have to observe out of the page, this is what would happen, right? So in this case, the pen will be coming towards you. So this is towards the observer. So in this case, what you'll be seeing here is the tip of the pen. Again, the observer, you are still here. And then right now, since the pen will be going out of the page, so like this is out of the page, and then now what you'll be observing is this tip of the pen. But then if you are looking at it going into the page, this is what you observe, the back of the pen X, right? So this is used to indicate the direction of the current. If the current is going into the page or inside, then we indicate it by showing the X, and then if it's going out of the page or towards the observer, we indicate by showing the dot, right? So now what we want to get here is the direction of the magnetic field. So for that, we're going to use the right hand rule, and this is what we're going to do now. For the right hand rule, when the current is going into the page, so when here we have this X, this is what we'll observe. So we'll hold out our hand like this, and then the thumb, remember in the right hand rule, the thumb indicates the direction of the current, and the curl on your fingers represents the direction of the magnetic field. So now the thumb indicating the current will now be facing down, and then if you look at the direction of the curl of your fingers, it is now in a clockwise direction, meaning when the current is going into the page or away from the observer, the magnetic field will be in a clockwise direction. But if the current is going out of the page or towards the observer, now what do we see? The curls of the fingers are in an anti-clockwise direction. So this is out of the page when you see the tip, right? And then this is anti-clockwise. The direction of the magnetic field is anti-clockwise, but then into the page the direction of the magnetic field is clockwise. So which one are we supposed to draw here? Remember, when we look at the question, we are shown the X here, so the one that we should draw here is for the one where it is going into the page. Now having to draw that, you just indicate that this is X, and then you can just draw maybe two of this, and then just indicate that the arrows will be in a clockwise direction. So this would indicate the direction of the magnetic field. And that's how you use your right hand rule to answer that. Okay, now we have 9.2.1. It says state Faraday's law in words. So Faraday's law states that the magnitude of the induced EMF across a conductor is directly proportional to the rate of change of magnetic flux linkage through the conductor. And that's how you have your 2 marks. Then 9.2.2 says calculate the magnetic flux linkage phi with the solenoid. So we call this phi the magnetic flux linkage. Now, having to calculate that one, let's first read the statement in 9.2. It says a solenoid with the radius of 5 centimeter, which from here we can see that we have a problem with this. Remember, our distance in physical sciences must always be in meters, so that means there's some conversion that needs to take place here. And then we are told that in 350 turns it's pulled out a magnetic field strength of 5.20 Tesla in 0.1 seconds. Now the solenoid is placed perpendicular to the magnetic field. 9.2.2 says calculate the magnetic flux linkage with the solenoid. Now we know the formula to go about with that one is this one. For the magnetic flux linkage, you say magnetic flux linkage is equals to BA cos theta. So having this one, the B here is for the magnetic field strength, which from the statement here we can see that we have that one. And then the A is for the area. So having to calculate the area, we know that a solenoid is circular. Then we know that the area, we have to calculate the area of a circle. Now the area of the circle is A is equals to pi times r squared. So now having to answer this question, first we want to calculate the area, pi r squared, but then remember our radius is 5 centimeter, which we need to convert to meters by dividing by 100. Then we have 0.05 meters. Then having to calculate the area, we have pi and then 0.05 square, right? Then if you punch that in your calculator, you have 7.85 times 10 to the exponent of negative 3 meters square. So you have your area like that in meters squared. Then I always prefer to write my area in terms of scientific form, right? Then to calculate the magnetic flux linkage, that's BA cos theta like that. Then what is your B? It's 5.20 and your area is 7.85 times 10 to the exponent of negative 3. Then we have cos. Then the theta here, if we read here, it says the solenoid is placed perpendicular to the magnetic field. But we know the theta that we are looking for, the angle that we are looking for, is not between the solenoid and the magnetic field. It is actually between the magnetic field and the normal of the magnet, right? So now if the solenoid is placed perpendicular to the magnetic field, that goes to say that the magnetic field will be parallel to the normal, right? So it will be parallel to the normal. So an indication of that will be this. If we put our magnet here in the solenoid, remember our magnetic field has to be in this direction, right? And then also the normal here will be in that direction, in that same direction, upward like that. So the magnetic field and the normal will be parallel to each other. If they're parallel to each other, then means theta is equals to 0 degrees. Then we have here 0 degrees. Then having to punch all that in your calculator, it will give you phi is equals to 0.04 Webers, right? Okay, so 9.2.3 says calculate the induced EMF in the solenoid. And to calculate that one, we have to utilize the formula E is equals to negative N change in magnetic flux over change in time, right? Then if we have to read the statement again, it says a solenoid with the radius of 5 centimeter and 350 turns. So this is the number of turns. It's pulled out a magnetic field of strength 5.20 Tesla in 0.1 second. So this is our change in time. Then the solenoid is placed perpendicular to the magnetic field. Okay, now we have this E is equals to negative N, and then change in the magnetic flux linkage over change in time. The N, we understand it to be 350 turns. And then what about the change in magnetic flux? We know that when we calculated, we were calculating the magnetic flux as the magnet is going inside here. So we calculated the magnetic flux to be 0.04 Weber in the previous question. But then as soon as the magnet leaves the solenoid, there won't be any magnetic flux linkage with the conductor, because right now the magnet is leaving the conductor. So now the magnetic flux will be 0 Webers. Having to represent that, so this is the final magnetic flux. Now the change in magnetic flux is represented as magnetic flux finally minus magnetic flux initial. So in that case, we have 0 minus 0.04, which will now give us negative 0.04 Webers. So at this point here, we will substitute negative 0.04, right? And then what is our change in time? Our change in time is 0.1. So always your change in magnetic flux should be a negative, so that it multiplies with this negative, so that you have an induced EMF that is a positive. Now if you punch all this in your calculator, you will have 140 volts. So that's your induced EMF.